Okay, let's look at chapter 19, which is modeling stuff with sine waves. So now we're going to do, they'll give you a problem. You got to model a periodic thing because sine waves go back and forth forever. And so they're really good at modeling things that vary, that go back and forth and back and forth. And things that's a circular function, right? That's all based on the unit circle. And things often change as a circle does. It starts off fast, slows down, like sine does, right? Sine starts increasing quickly in the beginning, because if you draw your unit circle, let me draw the unit circle up here. Sine starts off at 0, right? Sine is the y coordinate. It increases really fast in the beginning, and then slows down, and then starts speeding up and increases quickly, and then slows down, and just keeps repeating itself and repeating itself. And it turns out many things in nature do that. Masses on springs, bouncing up and down on springs, pendulums going back and forth. They increase quickly when they're going fast, slow down, and then start increasing quickly again. So sine waves are a good way to model things. And you don't really need a cosine wave. A sine wave is good enough because a cosine wave is just a sine wave shifted to the left 90 degrees. They're just, or pi over 2. So it's basically the same thing. Right, so I drew a picture of a typical sine wave here. Starts off at 0, and if we wanted a cosine, we just take this peak and shift it over here. So it's just a cosine wave that's shifted, and we know how to shift things. We can just take, like, here's our sine t. If we want to have a cosine of it, we shift it to the left, which means we add pi over 2. So sine t plus pi over 2, and that will shift it this way to the left, pi over 2. And that makes it a cosine wave. So we don't really need a cosine. We just can model everything as a sine, and if we want a cosine, we can just write it and shift it. So this chapter is all about modeling a periodic function with a sine wave. And so the most general way to do it is this formula, which we're going to be using a lot. This is why we studied all the shifting stuff, because then this should make a lot of sense. So if we look at this, A is the amplitude. That tells us how much we're going to shift it in the, in the y direction, right, this way. If A is like 2, it's going to be twice as big. I just drew kind of a sample sine wave here. For mine, our amplitude is 5 because it starts off right here at 10 and it goes as high as 5 and down as low as as high as 15 and as low as 5. So the amplitude, the number you stretch it by, we're stretching it by 5 because normally sine goes from 1 to -1. Right? It goes from the middle, it goes up 1. From my middle, it goes up 5. So for my wave here, it's going to be 5. That's the amplitude. How much bigger it is than 1 from the middle, right? Because it's always the middle of a sine wave goes to 1. The overall is 2 from 1 to -1. Here the overall is 10 from 5 to 15. So the amplitude is half of that, is 5. Okay, then sine, and then this tells you how much we're going to stretch it out, right? And so B here, this is kind of the confusing one, but it makes sense. B is the period, how long for a full cycle. And the way that makes sense is, let's say B was 2 pi, that's the normal period. If B was 2 pi, then 2 pi divided by 2 pi is 1, and it's just normal, which normal is a period of 2 pi, right? Our sine wave, typical sine wave, has a period of 2 pi. So if we put a period of 2 pi, that's 1 and we're done. Let's say B was 4 pi. Then 2 pi over 4 pi is 1/2, and we're going to stretch it out twice in the x direction, right? This tells us how much we stretch it in the x direction. So if B was 4 pi, that's 1/2. We're going to stretch it out this way by 2. Which makes sense because in the period it would be 4 pi, not 2 pi. So we'd take our sine wave here and we'd stretch it out to 4 pi. So it's kind of weird having the period in the bottom, but that still makes sense. So B is the period, and that again tells us how far we stretch it out, how far we stretch out our sine wave this way. If B is greater than 2 pi, right, we're stretching it this way. If it's less than 2 pi, this number is greater than 1, and it's always the opposite in the x direction, and we're going to compress it. And then C tells us the shift, how far we're going to shift it from the normal sine wave. Normal sine wave starts off at 0 and then goes up and goes below that. So if we want to move our sine waves off, we have to shift it. Okay, so my sine wave here, let's do this example. My sine wave here is a period of pi, right? So I made it so it starts at 0. No, actually, wait, it starts right here. Let's look at this. It starts going up here. Here's a normal sine wave. It always starts in the middle and goes up. So it starts at pi over 2 and finishes a complete one at 3 pi over 2, which is a period of pi. So we would say 2 pi over pi, which of course is just 2, times t, and the phase shift, I shifted it. It's now starting at pi over 2. So we shifted it. It should start here, but we started it to the right by pi over 2 because in the middle of it starts going up at pi over 2. So the phase shift here, it's over to the right pi over 2, which means we go minus pi over 2, right? When you shift things to the right, you take away. So that would be our phase shift. And then the d is the mean or the average of it. What is it bouncing around? Normally the mean is 0, right? We bounce around 0, go up above 0 to 1 to negative 1. Here we're going from 10 to 5 to 15. So the middle of it, and here it's obvious it's 10, but you just take the peak and the valley and divide by 2. Add them, divide by 2. So 15 plus 5 is 20, divided by 2 is 10, if the math wasn't easy. So our mean here was 10. That's what it bounces back and forth around. So that would be a representation of this sine wave, this random sine wave that I drew. And of course, this would be 2 here, right? 2 pi divided by pi, which tells us that it's compressed, right? If this number is bigger than 1, it's a compression, so it's actually compressed by 2, which makes sense. We took our wave here. Normally it stretched out a period of 2 pi. Now the period's only pi. We made it 2 times smaller, 2 times quicker together. So if this number is bigger than 1, the 2 pi over the period is bigger than 1, it's going to be wiggling back and forth really fast. And if it's a really small number, that means we're stretching it out, and it's going to be going really slowly. Okay, so this whole chapter then is going to be using this formula and figuring out what is A, what is the period, what is the phase shift. The phase shift is a tricky one, and one reason it's tricky is it can be multiple things. Because I said the phase shift here was pi over 2, because we took, normally again it goes up here, but we shifted it this way by pi over 2. But we could have said, well, no, it's starting here, because that's where sine wave starts. So really it could have been, we could have said, let's see, it's that distance, it's 3 pi over 2. We're starting it at 3 pi over 2 instead of at 0. So I could have said 3 pi over 2, or we could have said it starts here. I could have said 5 pi over 2. It's all the same thing. It ends up being the same math. Normally you choose the smallest one. It's just nice to choose the smallest one. Why go 3 pi over 2 or 5 pi over 2 when we could just choose the small one? But that's a little bit confusing part, because, you know, where do you start it? And since it goes back and forth, it's the same thing no matter where you start it. And that's just saying that sine of theta is the same thing as sine of theta plus 2 pi. Once we go around in a circle, once we get back 2 pi, we're starting all over again. So again, the phase shift here can be different, but normally you just choose the smallest one. All right, so that's the overall gist of this chapter. So let's do a couple of problems from 19.1. So let's say 19.1. Let's start off with A, since that's a good place to start. So we'll look at A, and they have sine of 2x minus pi plus 1. Okay, so we want to write it as this form up here. Okay, we want to write it as this form up here, and then we can pick out what A, B, C, and D are. Okay, so first thing, we want to get the x by itself. And sometimes, okay, here we're using t because when we do a lot of modeling, it's going to be time. Things usually vary as time, so I'm using t, but it could be x, it could be any variable we want. But most of the time, when we do actual problems, it'll be time going by and we use t. But in these problems, we're just using x, so it doesn't matter. Okay, so first thing here, we'll write it, we got to get the x by itself. So, because that's where it's always written, so sine of 2 times x minus pi over 2. And remember, this is why when we did in the earlier chapter, I always said get the x by itself and then graph it, because in general, that's the best way to do it. You don't have to if we're going to graph this, right? There's the way that some of the answer keys did it, they didn't do it that way. But because we're doing that now in other situations, it's always best to get the x by itself. And in this case, we have to figure this out. So 2 times x minus pi over 2 plus 1. Okay, now it's in the form that we want. Now it's in this form. So let's see. The amplitude, there's no a in front, which means it's 1. So the amplitude is 1. The period is going to be the tricky one. We have a 2 out in front. And we want to write that as 2 pi over b, right? So for the period, so I'm going to do my work down here, that 2, whatever number is here you're stretching it by, is 2 pi over b. Therefore, if that's going to be 2, this b in the bottom has got to cancel out the pi. Or we could just do algebra. You can just swap those two, right? You can always swap. One's the top, multiply both sides by b. You get the b here, divide both sides by 2, you get the 2 here. So b is equal to 2 pi over 2, which is just pi, which we could have seen right away. If b was pi, the pi's cancel, we get 2. Or we can also see that, oh, we are compressing it by 2. A normal sine wave is 2 pi. We're going to make it smaller by 2, so this one is pi. So b, our period, is pi. And then, let's see, the phase shift is pi over 2. And we got to be careful. It's minus, it's positive pi over 2. If that was a plus, it'd be negative pi over 2. And then the average is 1. So we're going to be bouncing up and back and forth around 1. So our average is 1 here. That's pretty easy. That's the one at the end. Okay, so that's how you do these. The only tricky part is whatever number is out here, you set that equal to 2 pi over b and solve for b. Or b, you can just think of b is always 2 pi divided by this number. If you're really clever, you can think of it that way, right? b is always 2 pi divided by whatever number is there. All right, let's do one that looks a little bit trickier, like f, and then you can practice the other ones on your own. F, they have y is equal to 3.9. Oh, lots of parentheses here. They're trying to fool us. Sine of, holy cow, 22.34 times x plus 18. And then minus 11 and more parentheses. Okay, I might need a calculator on this one. Okay, we want to write it as out of the way. So this minus 11 is inside here. So let's just multiply the 3.9 through. So we're going to have to know what 3.9 times 11 is. So 3.9 times 11 is 42.9. So this is the same thing as y equal 3.9 sine. And they already got the x by itself for us. So that's nice. So they did a little bit of niceness for us. 22.34 x plus 18 minus 3.9 times 11 is 42.9. Okay, so right away we can say that the amplitude is 3.9. The period's a tricky one, and if you remember, what do we say? It's always this number, 2 pi divided by this number. 2 pi divided by this number, or we can write it this way. I always like, that gets tricky in my head, so I just go 22.34 is equal to 2 pi over b, or b is, swap those two, 2 pi divided by 22.34. Okay, that's ugly. I'm not going to even try to keep that as a pi. Let's just decimalize it. 2 times pi divided by 22.34. I get about 0.281. Let's say 0.28. So about 0.28. Okay, so the period is 0.28. The phase shift, C, since this is positive 18, it's going to be negative 18. It's always the opposite. And then our mean is just this number at the end, negative 42.9. So if we were to graph this, it'd be pretty easy. It starts off at negative 42.9, and it starts to the right. It doesn't start at 0. It starts at negative 42.9 at negative 18. Okay, our phase shift doesn't start at 0, it starts at negative 18. So you'd go to negative 18, put a dot at negative 42.9, and then it goes up 3.9, and then down 3.9 every 0.28. It makes a full cycle every 0.28. So by 0.28, it's gone up and down and back here again. Okay, so it's a little bit tricky graphing it. But when it's in this form, it makes total sense. We can totally see what the thing does. It goes up and down 3.9. It starts off at negative 18. It averages at 42.9. It has and a period takes 0.28 to go make a full cycle. A full sine wave goes back and forth in 0.28. Okay, that's how you do 19.1. The other ones are then just using this formula, reading a word problem, and figuring out from the word problem. They give you enough information to figure out what A is, what B is, what C is, and what D is. And so it's always getting this formula for the problem, reading the problem and trying to figure out this stuff, which is tricky. These are tricky problems, so I'll do another example later of one of those doing the modeling. Okay, hope that helps. Bye.